We will begin speaking about annuities. In particular, we'll be looking at sinking funds. Now, anytime you have a sequence of payments over an equal time interval, for instance, if you're making monthly payments on something or quarterly payments on something, this is called an annuity. If you're contributing to some type of retirement, most likely it's in the form of an annuity. To calculate the future value of an annuity, we have a formula given to us. The FV stands for future value. PMT is your monthly payment or your periodic payment. It doesn't have to be monthly. And then the rest of this formula should look familiar to you. Again, the M stands for the number of payments per period in a year. And of course, T is always going to be time in years. So let's see if we can practice a little bit with this formula to answer these questions about annuities. First one says, suppose you deposit $1,500 each year for 15 years in a savings account that pays 4% compounded annually. How much would the account contain after 15 years? And then we'll calculate how much you actually contributed. Now, in order to see this amount, we're going to need to use this formula. So I'm going to copy the FV equals PMT, your payment amount, and then be very careful when you enter this in the calculator. This is the only thing that becomes a little tricky, is you have to really watch order of operations and make sure when you type this into your calculator understands what it is you're asking it to do. You might want to put an extra bracket around this point to show you've got to calculate all of this in that bracket before you would multiply it times the monthly or the regular payment that you're making. Now, looking at this problem, we're going to put in $1,500 each year. It's an annual amount that we're putting in. So, for example, if you were thinking in terms of, say, an IRA, you might only contribute once a year at the end of the year into that account. If we now plug in the rest of the information, our interest rate is paying 4% compounded annually. Well, if it's compounded annually, that means our M is 1. Only one time per year is it being compounded. So we'd have 0.04 divided by 1, which is obviously just 0.04, raised to the 1 times our T is 15 years. So it's going to be raised to the 15th power. Now notice you have to subtract 1 from that, and then the entire amount you just calculated will be divided by your R, which is 0.04, divided by M, which is 1. Now, at this point, you go to your calculator and start with this inside parentheses in the numerator. You're going to have 1.04, that's what you get when you add what's in the parentheses. Raise that to the 15th power, hit enter, get your answer, then subtract 1 from that. Hit enter again. And then take that number and divide it by 0.04. You're going to have a decimal number which you will then multiply times 1,500. And that should give you an amount of $30,035.38. And again, if you're having any calculator issues, please let me know. I'll be happy to help. We do still have this follow-up question, which is how much did you contribute? Well, the amount contributed is easy to calculate. They paid $1,500 each year for 15 years. That means $22,500 is what they paid in, and over the 15 years it grew to $30,000. Now, next question says Julia deposits $75 at the end of each quarter. For 20 years, the account is paying 2.8% annual interest compounded quarterly. We want to know how much is in the account at the end of 20 years. So we're going to set our formula in place. Future value is equal to PMT times, this numerator is 1 plus R over M raised to the MT power minus 1. All of that is over R divided by M. Now, let's see what we know and what we need to find out. Since we want to know the amount that's in the account at the end of 20 years, we are looking for the future value. The payment amount is $75. What I know about the interest rate is that it's 2.8% compounded quarterly. So remember, change it to decimal form. That's 0.028 divided by, if it's quarterly, that means it's compounded 4 times in a year. Raised to the M is 4, and we want to know how much will be there in 20 years. So we're going to multiply that times 20. Don't forget to subtract 1. After you complete that numerator, then you come back and you divide by your R over M, which is 0.028 divided by 4. Now let me just make a quick side note here. 2.8% is obviously very low, and I know right now you may be thinking, what can you do? The only amount that you can get if I put money in the bank is really low. Yes, that is true. However, if you will do a little shopping around and check on some different options, you can actually find better interest rates. Check with a place like Edward Jones, an investment advisor, or Merrill Lynch, or some of those places. And without getting into things that are terribly risky, you can find that you can actually get a pretty decent return even now while banks are paying such low interest. It doesn't necessarily take a lot of money, but it probably would take at least $1,000 to open an account and get started. So I encourage you, shop around, look for a good interest rate, and be smart about how you would invest your money. Now, while I've been saying that, I hope you have taken time to put this in your calculator. Let's see if your calculator skills are up to par, because you should end up with $8,006.36. That would be the future value if you make that $75 deposit at the end of each quarter for 20 years at this particular interest rate. Now, if I want to know how much she contributed to the account, what did she actually invest? Well, she paid $75 every quarter, so that meant 4 times a year for 20 years. And if you multiply that out, you'll see that she deposited $6,000. Now, over 20 years, for the $6,000 to grow to $8,000, that's because the interest rate is so low. If you were to go back and recalculate this with a higher interest rate, I think you'd be surprised at how much you could do in 20 years with a little better interest rate. Now, if I need to calculate how much interest actually was earned in those 20 years, all I have to do is take the difference between these two. So if I take $8,006.36 and I subtract $6,000 from it, I'm going to have $2,006 $2,246.36. Mr. and Mrs. Lopez have a new son. They want to start an account. It will be a sinking fund for his college education. So they're going to put $100 in the account each month. It's earning 5% annual interest compounded monthly. And they start this account when he's 2 years old. How much will be there when he is 18 years old? Obviously, you can see where this would be a really helpful thing to know and to understand how your money can work for you if you allow that compound interest to do its job over an extended period of time. Now, we still need our formula, FV equals PMT times 1 plus R over M raised to the MT power minus 1 over R over M. Now, you may be thinking, why do you keep writing this down every time? There's a couple of reasons for it. First of all, I need to be sure that I am plugging into my formula correctly by writing it down, copying it down each time. That helps me make sure that I don't make a mistake because I didn't look at it correctly. As long as I can copy it down correctly, that's going to help. Also, the more times you copy it down, the more familiar you become with it. And even though you will have access to notes on the test, you're going to find that it's much more helpful if you sort of have an idea of what the formula looks like before, excuse me, you actually have to find it on the sheet to copy it down. Now, since we want to know what will be in the account when he's 18, we're looking for the future value. They're putting in $100 every month. So that's our PMT. Now, for our numerator, 1 plus the interest rate they're earning is 5%, 0.05. And that's annual interest compounded monthly. So my M is 12. Raised to the 12 times, now here's the part I have to calculate. They started the account when he was 2. They want to know how much will be there when he is 18. So to get my time, I have to subtract 18 minus 2. My time is going to be 16 years. And then we'll divide that by our 0.05 over 12. All right, let's see what happens if you go to your calculator. Remember, always start with your inside parentheses. So you will need to take your 0.05, divide it by 12, add 1 to that answer, then you can raise it to your exponent, which is 12 times 16. Take that answer, subtract 1, then divide all of that by, and you'll have to use a parentheses for 0.05 divided by 12. Last step is to multiply that times 100, and the Lopez's will have $29,324.28 in this account when their son is 18. Not bad. Not bad. You can definitely see the advantage to planning ahead and taking care of that. All right, let's say you want to buy a house. John and Sally want to buy a house in 4 years. They need money for a down payment, so they're going to save $250 a month in an account. It will be a sinking fund that pays 5.5% annual interest compounded monthly. Let's see how much money will be there at the end of 4 years. So here we go again. We're going to be plugging in to this formula. Let me get it copied down. All right. They're going to put $250 a month. So that's going to be our PMT. The interest rate that they're earning is 5.5%. So our R is 0.055 divided by that interest rate is compounded monthly. So divided by 12. raised to the 12 times, they want to know how much is in the account at the end of 4 years. So my T is 4. Then we're going to subtract 1 from that. Take all of that numerator and divide it by 0.055 over 12. Okay, calculator time. Obviously you can see you do not want to do these problems without a calculator, and you need to be very comfortable and confident in how to use your calculator. If you get all of this entered in correctly, you will see that they'll have $13,388.21 in the account after 4 years. So John and Sally decide to get the size of the house they would like to have. They really need to save for a couple of more years. How much will be in the account if they continue to save for 2 more years? Well, the only thing that's going to change from the problem we did just a moment ago is we're going to change the value on the time. So we're still putting in $250 monthly. Interest rate is still 0.055, compounded monthly, so there's a 12 there. But now, instead of having it in for 4 years, they want to invest for 6 years. So we're going to have, excuse me, 12 times 6, or 72, as our exponent. That is the only change that we're making in this problem. So if you go back and you recalculate, instead of the $13,000 that they would have at the end of 4 years, giving themselves 2 extra years increases the amount that they have for a down payment to $21,268.35. So good to know how you can calculate if you're trying to accomplish a certain goal, like John and Sally were. Now, Mr. Johnson decides when he's 40 years old to start saving for retirement. I'll just mention, if you've seen those commercials on TV where they talk about when should you start saving and people don't start soon enough, this is a prime example. The way compound interest works is the longer that it sits and has time to grow, it will take probably about 20 years before you see that growth really take off. Remember, you're earning interest on top of the interest that you earn. And so you've got to have enough time for that interest to be added into what's there to really make a difference and to see it grow quickly. So starting at 20 is a lot better than starting at 40, but you got to start sometime. So even if you're 40, go ahead and start now. What he's going to do is deposit $200 in a month into an account that pays 3.75% compounded monthly. So he needs to know how much will be there if he wants to retire at 60. What if he waits till 65? What about if he does it at 70? So again, it's the same question. The only thing that's going to change is going to be the length of time that this money is going to be able to grow. So if we plug in, and I'm just going to write this down one time since we're going to be using it over and over. Here's our formula. All right, if he's 60, he's putting in $200 a month. His interest rate is 3.75%, so that's 0.0375. Compounded monthly is a 12. Raised to, M is still 12. Now, if he's 40 when he starts this, if he wants to retire at 60, how many years has his money been invested? Well, that's 20 years. And then all of that gets divided by the 0.0375 over 12. Okay, if you calculate that, and again, always start with your inside parentheses, so you'll have to do 0.0375 divided by 12, take that answer and add 1, raise that to your exponent is 12 times 20, which is 420. Take that answer, subtract 1, divide it by 0.0375 over 12, and you have to be sure that after you hit divided by, you open up a parentheses before you type in 0.0375 over 12. And then that answer is going to be multiplied times 200. You should have $71,329.65. Okay, that doesn't sound too bad, but I want you to see the difference that adding a few more years would make. If he waits until he's 65, the only thing that's going to change is right here. Our T will no longer be 20. T will equal 25. Everything else about this formula is identical. He's still putting in the same monthly amount. He still has the same interest rate. We're just leaving it in for a longer period of time. And so instead of having an exponent of 240, if you multiply 12 times 25, you're going to get 300 for an exponent. And I want you to see that that would end up being $99,191. Not bad, okay? But look at the difference if he goes 5 more years. If instead of only having invested for 20 years, let's see what happens if he goes to 30 years. In this problem, our T would equal 30. So everything from up here is the same, except we're going to put 30 in for T instead of 20. Mr. Johnson now has $132,788.37. I want you to notice that the additional 5 years from 20 to 25 added $28,000 to the amount that he had in his account. But notice the next 5 years, going from 25 to 30 years of investment, actually added $33,000. That's, you can see that it's adding more over the same period of time the longer you go. And if you actually went an additional 5 years, I think you'd see an even bigger jump. What would make this problem even better is if the interest rate were higher, and you would see an even more significant difference in the increase whenever you would go up the extra amount of time at the end. All right, one more example, and on this one, instead of looking for the future value, we want to find out what would be that regular payment that needs to be made. So we have a couple, they want to have $40,000 in their child's education account, and they want to know how much would they need to put in each quarter if the account is earning 4% annual interest compounded quarterly. And they're going to begin saving when their child is 5, and they're expecting their child to begin college when he is 18. So, same formula, it's just now we're going to be plugging in a little differently because we're not looking for the future value. We're going to be looking for that regular payment. So I'm going to copy down my formula. And we're going to plug in the pieces that we know. We know they want to have $40,000. So that's what the future value should be. We're looking for this regular payment amount. So PMT is our variable here that we do not know. Now, if I plug in the rest of the information, the interest rate is 4%, so that's a 0.04, and it is being compounded quarterly. So I'll put that over 4. Raise it to, my M is 4, and my T I have to calculate. If the couple begins when the child is 5, and he's going to start college at 18, I have to subtract. T is equal to 18 minus 5, which is 13. So for 13 years, this is what they're going to do. And then we'll divide that by 0.04 over 4. Okay. We can calculate everything inside this bracket. We will need to do that first. So just like we've been doing, use your order of operations, put that in your calculator, and you're going to come up with a decimal number that will be something like 67.76889. It actually keeps on going. You can either write down all the digits that you can, or you can retain that in your calculator, because what we have to do to find the payment will be divide both sides by that 67.76889. And remember, we want to round this to the nearest cent. The monthly payment needed is going to be $590.24.